Hi, I'm Scott, and in this video I'm going to demonstrate a motion control slider that I made. Where are you going? In this video, I'm going to demonstrate a motion control slider that I put together. This one right here, actually. It's based on one of the cheapest sliders available, and it has a stepper motor hanging off it that's connected to an Arduino. And that's in this rather large controller, along with user interface components. Besides just moving the sled back and forth manually, the controller can record and play back a series of movements and speed changes, so it can do its thing without having someone to operate it. So, why a motion control slider? Mostly I made it for fun, but the original impetus came from an HPRC Pelican review. Towards the end of that video I had a sequence which showed gear being unloaded from the Pelican. Check it out in full size. The transitions aren't very smooth and there's tons of artifacts in that last shot. That's because I don't have the steadiest hands in the world. I did 4 or 5 camera passes at 4 or 5 different speeds. It was one of the last shots of the video and I got lazy. Rather than reshooting, I just threw a warp stabilizer effect on it. That smoothed out the apparent speeds, but it introduced all the artifacts. So instead of using my own shitty hands, I figured I should just build a machine to do the same job. Now here's a reshoot with the HPRC case being unloaded using the motion control slider, and it's much smoother. Besides shots like that, motion control is just the ticket for stop motion animation, shooting in different settings for later composition, or just act as camera operator when you're a one-man show like me. Here's a slow motion shot of me dropping some RAM on the table. It was recorded at 60 frames per second, but you're seeing it at 24 FPS. Listen, this was my first real Arduino project, and I'm far from a mechanical or electrical engineer. I'm going to be telling you how I did this, but it's not necessarily the right way to do it. If you go to s.co.tt/mcslider, you can download my plans, source code, and a materials list to make your own improvements. If you do, please let me know. First, here's a look at the slider itself. It's pretty simple. Those aluminum bars, the timing gears, and the motor, all the mechanical stuff, are from a make block kit. The switches came from Amazon, and it's wired up using plain old Cat5. My first mistake, and I made a few, was not planning where to mount the interface box, which is why it's just sort of hanging there. But anyway, the box has a microstep driver attached to it, and all it's inside are some wiring splices. It interfaces with the controller using an old-fashioned DB25 male-to-male cable. The controller is an oversized ABS plastic housing with power and slider connections, a power switch, a potentiometer to control speed, a 4-row 20-column dot matrix LCD, and 6 buttons to control movement, recording, and playback. If you're interested in details of design and assembly, I made a narrated companion video which shows the entire process from start to finish. It's time-lapse, so you don't have to be completely bored out of your mind as I screw around trying to figure out how to put everything together for hours on end. Anyway, here's how it works. The camera attaches to the carriage or sled, whatever it's called, as usual. As soon as it's turned on, the controller goes into calibration mode. At each end of the track are micro switches that are closed when the sled hits them. First it finds one end, then it travels to the other end, and then back again. The number of steps in each direction is counted, and if they differ by more than 1%, the controller throws an error. This is to ensure that the whole thing is mechanically sound and that the sled isn't binding up. Once it's calibrated, the sled should never actually hit either end switch. If it does, the motor will stop immediately. At this point, the stop button is lit and the display says stopped. Pressing reverse will of course start the slider moving in the reverse direction. When I designed it, I first labeled everything left and right, but then I realized that it would be confusing if you're standing on the wrong side of the slider. Forward and reverse aren't really much better, and I guess if I had to do it again, I'd label everything right to left, but I'd implement a switch that programmatically changes which is left and which is right. So, as you just saw, the slider stops automatically when it gets close to the end. Of course, you can stop it manually or change direction mid-motion. The slider pot does pretty much what you'd expect. When it's set all the way to the right, it's at maximum speed. All the way to the left, and it's at 0. It can be adjustable while the slider is moving or beforehand. One difference is that if you adjust the speed when the slider is stopped, it will update the display with that speed in inches per second. That allows you to match new moves with previous moves. Unfortunately, calls to the LCD library are a bit heavy, and they create a noticeable jitter in the movement of the stepper motor. If I could do it all again, I'd have used either a Raspberry Pi or 2 Arduinos, one to drive the interface and one to drive the motor. The lock button next to the potentiometer will lock the speed setting so that it remains constant even if the pot gets jostled. I added the bounce feature in case I wanted to have the camera sweep the same subject repeatedly. In fact, it's the way I shot the case unpacking sequence. It's also kind of cool. As you can probably guess from the name, it moves the camera between the two ends over and over again. I guess the coolest part of the project are the record and play buttons. When record is pressed and lit up, any change to the camera's movement is saved in memory, along with a timestamp. Basically, it records when forward, stop, or reverse are pressed, and records any changes in the value coming from the speed potentiometer. Since it's based on time to millisecond precision, you can have camera moves match tightly to a planned sequence. The record button toggles recording on and off, but hitting play will stop recording and go directly to playback mode. Once you have a sequence of moves recorded, pressing play first moves the slider to the same position it was in when the recording started. It then begins the set of movements. Playback can be interrupted at any time by pressing the stop button. The decal on the case may not be the best looking in the world, but it beats my original idea of just using a label maker. I designed it in Photoshop and printed it from my inkjet onto a full-page translucent Avery label. If you go this route, I'd recommend getting a white vinyl label. I thought it'd be cool to have the gray of the case show through where it says Scott, perfect color match and all, but really it just made the rest of the printed sections appear that much duller. There's a couple other things I would have done differently in hindsight. I'd have put the power input on the interface box rather than the controller. After all, the slider is going to stay in place during a shot, but I might want to move the controller around when setting up. I would have also used a lighter, more flexible cable in this 25 conductor behemoth. And I was kind of in a hurry to get this project started, and the project box for the controller was the closest one I could find to the size I needed, but obviously it's bulkier than it has to be. If you're building one, hold out for a better box. I also screwed up the size of the interface box. Originally I bought a stepper motor driver that would fit in there, but it was completely the wrong type. That's why the microstep driver is just sort of piggybacked onto the outside. The connections from the motor and the micro switches to the interface box could also benefit from removable connectors. RJ11s or RJ45s would work great. Not using them was just sheer laziness on my part. I couldn't find a reasonably priced timing belt that was long enough and that shipped from the US, so I just stapled a couple together. It's not as bad as it sounds. The staples have actually been holding up pretty well. And the stepper motor can be pretty loud depending on the speed. I wanted to have it wrapped in foam when I was shooting the opening of this video, but that's not a good solution if you're using it a lot. The motor will overheat pretty quickly. And again, I should have implemented this with 2 Arduinos or a Pi. In order to have the motor actuate smoothly, I had to set the microstep driver to 3200 pulses per rotation, which is 16 times the motor's speed of 200 steps per rotation. Asking the Arduino to process user I/O as well as accelerate, move, and decelerate without jitter is a challenge. I had to make some compromises like only updating the LCD when it stopped and reducing the resolution of the speed control and button pull intervals. Despite all that stuff I do differently, I still think the project came out pretty well. There are things I'm happy with, like the layout of the controls, the simplicity of the external cabling, and of course its overall functionality. It does what I wanted to do from the start, and I didn't have to make too many compromises. If you want to make your own version of my motion control slider, you can find everything at s.co.tt/mcslider, like circuit diagrams for the controller and interface box, a parts list, the controller decal template, and the full assembly video. Thanks for watching. I hope this gave you some good ideas to create your own motion control camera slider.